Okay, let's delve a little bit deeper into spontaneity here, and let's refine or go a bit deeper. Okay, so there's four types of reactions which cover our spectrum of reaction spontaneity. Previously, we just learned, Gibbs free energy. If it's less than zero, it's spontaneous. If it's greater than zero, it's non-spontaneous. Let's refine that a bit more. If it's much less than negative 10 kilojoules per mole, it is spontaneous. So we've changed that flag post, okay? But hold on. Reactions that occur after an activation energy is supplied are usually exothermic reactions, so such as combustion reactions of magnesium. These ones are also classed as spontaneous as well because they're just below the 10 kilojoules per mole mark, okay? So for them to get going, you need a large input of energy. So think about when we burn magnesium, we need to put it under a really hot flame, give it a lot of kicker energy, and then it will go, okay? We've kind of got this kind of fuzzy area. Yeah, I might call it a bit of a fuzzy area. So before, where we had the 0 point, which is halfway in between our negative, I've scribbled over the negative, haven't I? But we've kind of got this fuzzy area here. There's a range between negative 10 kilojoules per mole up to positive 10 kilojoules per mole. So it encompasses that 0 that we used to think was the goalpost, where both the forward and the reverse reaction occur to some extent. So you can flip the enthalpy side and it doesn't change the Gibbs free energy much at all. Just a little positive to a little negative kind of thing. What it means for these reactions that have a small Gibbs free energy within the positive and negative 10 ranges is that both of the forward and reverse reactions are somewhat spontaneous and occurring when you put them together. Okay? These reactions are kind of special, and we give them a name called equilibrium reactions, and I'll talk about that in a second. So reactions, even where elevated temperatures will not make the reaction occur, usually have a Gibbs free energy of greater than positive 10 kilojoules per mole. So you know, if you're getting positive 10 kilojoules per mole and over, yeah, there's not much that you can do. That's not happening. Okay? So this kind of funny kind of grey range between negative and positive 10 kilojoules per mole. These, as I was just saying, both the forward and reverse reaction is somewhat around the kind of the goalposts of the spontaneous. So you get both the forward and reverse reactions happening at the same time. And we give these a special name called equilibrium reactions. And they have this funny thing where they go in the forward reaction and it happens in the reverse reaction, all in a mixture, and it seems to stop. Unlike normal reactions, or how we normally think about doing, you put the two reactants together, everything reacts, and you go convert all over to the products, apart from if you've got something in excess. These equilibrium reactions don't do that. They stop. They seem to stop earlier than that when there's a certain concentration of the reactants still there and there's a certain concentration of the product still there, but it doesn't seem to be occurring anymore. So the rate of reaction over time for the forward and the reverse reactions, well, the reverse starts up and the rate of reaction for the forward decreases, but they kind of reach a non-zero point and they stabilize, and we call this a chemical equilibrium. We're not going to go too much into it now because that is Module 5, equilibrium reactions. Okay, so there's some board work there to help you out. Now we also notice that temperature affects our spontaneity because temperature is a variable here in this reaction, in our Gibbs free energy reaction. Enthalpy and entropy are kind of set by the reaction that we're talking about, but our temperature that we conduct it at is not set. So under certain conditions, we can change temperature, which will suddenly change the spontaneity of the reaction. Okay? So here's kind of a table what we've been looking about earlier. We've got our four cases here. So if enthalpy is negative, or it's got the enthalpic drive, and entropy is positive, so it's got the entropic drive, we're going to get, for our Gibbs free energy, a negative minus a positive, okay? Negative minus a positive is always going to give us a negative value. So these reactions are always spontaneous, okay? No matter what temperature. Because a negative, let me draw it on here, a negative minus a positive, and because T will always be positive, of course, you can't get lower than absolute zero. So negative minus a positive for this term is always going to be negative. Negative minus something is always a negative, okay? So these conditions are always spontaneous, okay? Now let's look at the condition of our enthalpy is positive and our entropy is negative, okay? T will always be positive. So here in this condition that we can work out and look at Gibbs and go, well, a positive minus a negative is going to be a positive and a positive. There's no way that that's going to go negative, okay? It can't be spontaneous. So we say under those conditions, it's always non-spontaneous, no matter what the temperature is, okay? So these are our two conditions where our drives are opposing. So here with our delta H negative, we've got an enthalpic drive, but we haven't got an entropic drive, okay? Or another way to think of it is up here in the equation, which I prefer to do, is a negative minus a negative is a negative and a positive. A negative and a positive together. Could that be negative or could it be positive? It depends how big your negative and your positive are, really, isn't it? Okay? Now let's look at the other example, which is quite similar. This one here. So our delta H is positive and our delta S is positive. So a positive minus a positive. Is it going to be less than zero? It depends. Depends if the other positive is less or more. It depends on the size of these positives, okay? 3 minus 2, well, that's still positive, but 2 minus 3, that's a negative. Depends what's bigger, okay? So it depends on the temperature. So let me just erase this and I'll talk about more about the two funny cases where we have to determine it, okay? And we'll relate it back to temperature. So our funny case here and our funny case here that are not always something, it depends. Okay, let's talk about it a bit more. Maybe I might change color, pink. Okay, so for my delta H is negative and my delta S is negative. Okay, so a negative minus a negative is a negative and a positive. Well, that could be positive. So I'm starting like less than 0, and I might not get to 0 if T delta S is really small. Okay, I can't change delta S, but I can change the temperature. So if my temperature is really, really small, this will make this one negligible, and my enthalpic drive will win out. Okay, so what this is saying is that under these conditions, where you've got the enthalpic drive, but you're going against entropy, if temperature is small, it's still spontaneous. So that's why I've written spontaneous at low temperature here, okay? Because it makes this so small that we might not get above 0. So it's spontaneous at small temperatures. Okay, let me erase that one and we'll look at our other funny one here. Delta H is positive and delta S is positive. Okay, a positive minus a positive. Okay, if the only thing we can change here is to T. So if T is really small in this case, a positive minus a small positive is going to be positive. Okay, but as we increase T and T gets bigger and bigger and bigger, the minus T delta S gets a bigger and bigger number, and it's more and more likely to overcome the enthalpy value and turn Gibbs free energy to be negative, okay? So under these conditions, high temperatures are going to be positive. So under these conditions, spontaneous at high temperatures. All right. I think that's just a There we go. That's just another summary of what we've been talking about there. And here it is in words. So if entropy is positive, it's entropic drive, and so Gibbs free energy decreases or gets more negative as the temperature increases. Or for entropically driven reactions, heating it will cause it to become more spontaneous. Let's contrast that. If we're going against the entropic drive, or entropy is negative, Gibbs free energy increases as the temperature increases, or we want to lower temperatures to be spontaneous. Okay. If entropy is small in comparison to enthalpy, then the Gibbs free energy will not change much with temperature. And also, if the entropy is large compared to the enthalpy, the Gibbs free energy will change very large in temperatures. Okay, that's if you're very wordy and not very mathematical. That's why I put those slides there. I'm reading those going, having to really think about it. For me, the mathematical way seems more familiar in dealing with the formula. But if you're a more wordy chemist, that might help you out. Okay. Here we go. Past paper questions. If an endothermic reaction, or delta H, is greater than 0, is spontaneous at temperature T1, but non-spontaneous at temperature T2, which statement is true? Okay, so let's put in Gibbs and start thinking about it. So we know from the question that that is positive. Okay, so if we've got a positive entropy minus some other value here, minus the entropy value here, if that is large, it's going to be spontaneous. Okay, for that to be large, we need a large T, or spontaneous at high temperatures. We refer to that, not as large temperatures. Spontaneous at high temperatures. Okay. Okay, so it's saying it's spontaneous at T1, so T1 is high, and not spontaneous at T2, so we're saying that T2 must be a low temperature. Which statement is true? Okay, so we've already, if it's endothermic, enthalpy must be greater than 0. Let's get a red here. Okay, so enthalpy must be positive. Okay, so we can get rid of C and we can get rid of D because they say it's negative. Okay, and we've just seen here that temperature 1 is high and temperature 1 is low. So this one, not this one, is the winner. So this one's A. Okay, I like that question. It's a good one. It is a little bit difficult too. Look, it's number 19 out of 20. So feel a sense of achievement if you can get that. Okay, the equation for the decomposition of calcium carbonate is given below. At 500 degrees Kelvin, delta H for this reaction is this number and entropy is this number. Calculate the critical temperature for this reaction and state whether it is spontaneous or say whether it is spontaneous at higher or lower temperature. Should I put that there? It makes more sense. Okay, so given the entropy and enthalpy, we're asked to find the critical temperature where it changes from positive to negative. Okay, so what we're going to do is pull out our Gibbs free energy, and what we're going to do is say that critical point is 0. So we're going to set 0 equal to our enthalpy, which is positive 177 kilojoules per mole. And it's going to be minus some T, and we're going to solve for this T, times it by I want to align my units, so 0.161 kilojoules. Go away. Per mole per Kelvin. Okay? Alright. So what I'm going to do is... I'm thinking about this way too much. What I need to do is put T on one side. So I'm going to add T times whatever on this side. So T times 0.161 equals 177. Okay. And so T equals 177 times 0.161. Oh, I'm paranoid that I haven't done it right. No, that seems good. Okay. Oh, hang on, have I? No, I haven't done that right. You're all screaming at me right now. It's T. If I want to get rid of the multiply by 161, I've got to divide it by 0.161, haven't I? What a duffer. And that's my Kelvin. Okay. 177 divided by 0.161 equals 1099.37 Kelvin. So that's my critical temperature there. Let's just call it 1100 or 1099. Okay, is it spontaneous at higher or lower temperatures? Okay, let's have a look. So we had a positive... Did we? Yeah, we had a positive enthalpy minus a positive, okay? So as T increases, that second positive will get bigger and it'll become more likely that delta G is negative or spontaneous. So it's spontaneous at high temperatures. So it's spontaneous above 1099 Kelvin, and it's non-spontaneous below it then. Okay. Alright. Hopefully that problem helped you out. It's quite a hard one, actually. Those ones don't come up too often. And I think we're at the end of the chapter. Need more help? There's some helpful people, and we're all done. And that's the Year 11 course. Okay.